Hello, I'm Norman Wildberger, and today we're going to make the transition from two-dimensional geometry to three-dimensional geometry. It's a big step, and it's not an easy step. It's a challenge for many people to get good intuition about how three-dimensional geometry works. But of course it's very important because the world that we live in is three-dimensional, and applications to engineering, physics, architecture, and so on are obviously three-dimensional many times. Today's lecture we're going to be easing into this subject, so I'm going to show you some models and draw some pictures, and we're also going to have some philosophical things to say about the nature of space and how we represent it mathematically. This little thing here is a three-dimensional analog of what we've been drawing a lot of in two dimensions, namely our pattern of parallelograms on a page. Instead of having parallelograms in a plane, we now have parallel pipeheads in space. Of course, there's only a few of them here. This is actually just part of what you should imagine as an infinite pattern extending in all directions. And I'll move it around a little bit so you can get some sense of it. You can see that it's created by parallel lines in three different directions. There is a blue direction, and there's a yellow direction, and there's a red directions. And in fact, the entire pattern is generated by three basic vectors. For example, if we choose, say, this point here, and look at the three vectors that are emanating from that point, a blue one, a red one, and a yellow one, then the entire pattern is really constructed by just repeating those three vectors over and over and over again. This is a really good starting point for thinking about space because it naturally leads to the idea of arithmetizing space, or in other words, thinking about space as connected closely with numbers. And how that goes is by thinking that an arbitrary point or an arbitrary vector in the space can be thought of in terms of how it's built up from these three basis vectors. So let's say we choose arbitrarily the blue one, and then the yellow one, and then the red one in that order. Then say to get to a point like here, we would go up 2 in the blue direction, over 1 in the red direction, and over 1 in the yellow direction. So the vector from here to here, that vector there, would be represented by the triple 2, 1, 1. That allows us to associate to a point, or to a vector, a triple of numbers. And that's how we're going to think about what three-dimensional space is. Now it's important to observe that in this model here, the lines are not necessarily perpendicular. So we're working in an affine situation where perpendicularity plays no role. Also, it's not necessary that these vectors have the same length. In fact, there's no notion of length in affine geometry. It's not important for us at all. We could alter the positions of these vectors and their orientations, and we would get a different configuration, but mathematically, from affine geometry point of view, it would be completely equivalent. Now, working with a model like this is very pleasant, but it is a little bit cumbersome and fragile, and we want to be able to represent a three-dimensional situation on a two-dimensional piece of paper. So that's what we're going to talk about now. How do we represent something like this in two dimensions? There are two standard ways of representing a three-dimensional situation or scene in two dimensions. Both of them are called projection. And one of them is a perspective projection, where we draw lines emanating from some fixed external point to the three-dimensional object in question, and then connecting further on to our actual two-dimensional plane of viewing. And the other one is a parallel projection, where it's the same kind of idea. We have a three-dimensional object that we want to visualize, a two-dimensional visualization plane, and then we think of lines emanating from some distant source, which are all parallel. So all these lines are parallel, and we just use these lines to connect points in the three-dimensional object to our two-dimensional plane. It's important to realize that there are these two different ways of representing things, and they're quite different mathematically and visually too. This is perhaps the most familiar to us because that's the way our eye works, and our minds are quite used to interpreting what happens in a picture like this. So I've shown you a house here and our perspective projection of the house, and here is supposed to be a railway track that's beside the house. This is 3 dimensions here, and over here is our picture of it. The railway track, which has equally spaced ties, gets represented by 2 lines which converge to a point at infinity on the horizon. And the equally spaced ties become not equally spaced. They become closer and closer together the further away you go. So that's one of the properties of this perspective projection, that there's first of all a horizon, that lines which are parallel in the 3-dimensional object end up intersecting on that horizon. And that furthermore, equally spaced points in the original object do not get mapped to equally spaced points in the picture. The parallel projection has quite different properties. First of all, there's no horizon, and importantly, parallel lines map to parallel lines. Let me try to explain why that is. So suppose that our viewing plane happens to be the wall here, and that our 2 parallel lines are, say, these ones here. Okay, there's 2 parallel lines. And let's say that we put them at some angle to our wall. And suppose that the light beams that are coming in are represented by a vector, say something like this. So all that we're talking about light coming in all in this direction here, and then the image projected onto our board. So what's actually going on there is that if you imagine this fixed vector representing the direction of the light, then together with one of these lines, that fixed vector creates a plane. And with the other line, it creates another plane which is parallel to the original plane. So just imagine those 2 planes. Those 2 planes are infinitely extending and they're parallel. That means they do not intersect. So what is going to be the image of these 2 lines in this parallel projection? It's simply going to be the intersection of those 2 planes that I've just been talking about with the plane of our wall. So imagine those 2 planes intersecting the wall. The planes are parallel. So the image, or their intersections with the wall, are going to be parallel lines. Why? Well, because they can't meet. They don't meet here. These planes do not meet. And so the intersections with this wall are also not going to meet. That's a reason why, under parallel projection, the image of parallel lines is another set of parallel lines. And the other important point is that equally spaced points stay that way. So for example, here's railway track. Under parallel projection, we get another picture of a railway track, but the lines which were parallel become lines which are still parallel, perhaps in a different direction, of course. And these equally spaced ties are represented by equally spaced ties here. Both of these projections are mathematically very interesting and important, but when we start out with linear algebra, we are going to use this parallel projection. Why? Well, because we like these 2 properties. That parallel lines go to parallel lines is very nice because affine geometry is all about parallel lines. And the fact that equally spaced points are represented by equally spaced points is also practically very useful. Later on in the course, we're going to talk a little bit about perspective projections, and they're also very important, but for a different reason. But to start off with, we're going to think about parallel projection. That's the way we're going to represent 3-dimensional objects in a 2-dimensional picture. So let's give an important initial example of this idea of representing a 3-dimensional object in the plane using parallel projection. So the object that we're going to start with is a piece, just one box or one parallelepiped from that bigger pattern that I showed you earlier. So here is just a basic box created by three vectors. A blue one, a red one, and a yellow one. And these vectors are repeated. So this vector here is the same as that vector, same as that vector, same as that vector. There's 4 equal blue vectors. There's 4 equal red vectors. And there's 4 equal yellow vectors. So each of the sides of this box is itself a parallelogram. And this parallelogram and the one on the opposite side are equal. This one is equal to this one, and this one is equal to this one. I'll let you have a look at it there. Different. Now we want to represent something like this in 2 dimensions. So what are we going to do? Well, let me line it up like this. So if you have a look at it in this configuration here, then hopefully you should see something that looks like this. The fact that all these lines here are parallel is represented by the fact that these lines here that we've drawn in black are all parallel. And the 4 here are parallel, and these 4 red ones are also parallel. Okay. So the various parallelograms representing the sides of the box are represented here on the page also by parallelograms. Okay. So there's one side, there's the opposite side there, there's the bottom of the box, there's the top of the box. You should think of this point F as being towards you. Okay. So this FGCB side is the one closest to you. That's like this side right here. And this point O is the one back here. It's behind you. Okay? And so these 3 vectors emanating from O in the picture, which I've been calling E1, E2, and E3, they are like E1, E2, and E3 in our model. So there are a number of simple things to say about a parallelepiped. First of all, it has 6 sides or faces. We've talked about them already. It has 12 edges, 4 of any one kind, and there are 3 different kinds. So 4 times 3 is 12. And there are 8 corners or vertices. Now there are actually some other interesting aspects to this parallelepiped. There are actually some other parallelograms and other lines floating around. For example, with this particular labeling that I've got here, if you look at the points D, F, B, and O, that's also a parallelogram. We're talking about this parallelogram right here. It's a kind of a diagonal parallelogram for the parallelepiped. But that's not the only one. There's also this one here. And then there's various other ones. There's this one here. In fact, whenever you take 2 opposite vectors, which are equal in this picture, say that red one and that red one, then they determine a parallelogram. So there are also these edges that are joining corners of sides. They're like diagonals of the faces. But there are also some longer diagonals joining corners which are opposite in the parallelepiped. So for example, from B to D is a long diagonal. From E to C is a long diagonal. From A to G is a long diagonal. And from F to O is a long diagonal. And it's an excellent exercise to write down for yourself in terms of these basis vectors E1, E2, E3, how the various diagonals are represented. So to give you an example, suppose that we want to go from G to B, that vector from G to B. How would we represent that? Well, to go from G to B, we would go down here and then across here. What is this vector here? Well, it's opposite the vector E3, so that's minus E3. And this vector here is the same as this one here, which is E1. So this is minus E3 plus E1, or in other words, E1 minus E3. So this vector from here to here is E1 minus E3. And similarly, if you want to go from O to F, that would be E1 plus E3 plus E2. So that's the sum of all 3, E1 plus E2 plus E3. And here's another good exercise, is to show that the long diagonals, like the ones from joining O to F, that those long diagonals all intersect. In fact, they all bisect each other. Okay, so there's a central point right in the middle of this parallelepiped, which is the middle of all the long diagonals. You can see that a parallelepiped is a much richer object than a parallelogram. This is a reflection of the fact that three-dimensional geometry is just a lot richer and maybe a little bit more sophisticated subject than two-dimensional geometry. So usually when we represent three-dimensional space, we don't concentrate on one particular parallelepiped, but we rather concentrate on the three vectors which form it and the lines through those three vectors. So let's look at the point O with vectors E1, E2, and E3 emanating from it. And it doesn't really matter which directions they are in and how long they are. What's important is that they are in three different directions so that they're not all in a plane. Now, as long as they're in three different directions, then we can use them to establish a coordinate framework for three-dimensional space. And how does that go? Well, I'm drawing the lines generated by those three vectors and calling them x, y, and z. So when you see a picture like this, it's sometimes a little bit hard to interpret where things are. So it's useful to have a standard way of thinking about this. And that's to think of the E1 vector as, say, being in that direction there. This is the origin. And then the E2 vector coming out like that. So there's E1 and there's E2. And then there's one more, say the E3 vector like this. So there's E1, E2, E3. When you're looking at a picture like that, I want you to think of three vectors in this configuration. This is sometimes called a right-handed configuration because the vectors E1, E2, and E3 correspond to the first three fingers of the right hand when we extend them roughly at 90 degrees. But for us, that's not going to be that important because the vectors don't have to be perpendicular. They can be at angles, and they actually can be in any configuration that they want to be. Another way of thinking about it is to think in terms of a corner of a room. That you have a room here with this as being a corner. And that's one edge of the floor, that's another edge of the floor, and that's the side of the wall coming up. So we use a framework like this to represent general vectors in terms of coordinates. For example, suppose we take the vector E1 and we add to it the vector 4 times E2. So there's E2, there's 4 times E2. So if we take E1 plus 4 times E2, that would be that vector right there, because that's a parallelogram. Okay. And now suppose we add to it the vector 2 times E3. There's E3, so there will be 2 times E3. So if we add it to this vector 2 times E3, we end up here. So the cumulative effect of going E1 and then 4 times E2 and then 2 times E3 is to go from here to here. So this red vector, call it V, is E1 plus 4E2 plus 2E3. And that's how we represent it in our three-dimensional picture by drawing a little parallelepiped whose sides are parallel to the coordinate axes. Okay. This is a very useful technique. All what you have to be able to do is to draw lines which are parallel to the three axes that you started with. Okay? So E1, 4E2, 2E3, and then you just draw lines which are parallel to the ones from the coordinate axes. And you get that box or parallelepiped, and that corner of the box then represents the vector V. Now diagrammatically, we could use either of these two notations to represent that vector. We could say, well, we could represent it by the row vector 1, 4, 2, or by the column vector 1, 4, 2. It's purely a matter of notation or taste, what we're going to do, but we're basically going to stick with this column vector idea because that's what we've been using in our discussion of linear transformations in 2 dimensions. Okay? So for us, we're more or less going to use a column vector like this, 1, 4, 2, to represent that vector there. In our discussion so far, we've been rather relaxed about what the actual nature of space is. It's a quite subtle and delicate question, because the space itself in which we work and play is hard to get its hands on. What we can do is we can manipulate objects in space, and a lot of our intuition about what space is comes about by observing how things in space move around. The actual nature of space, when you take objects out of it, is very hard for us to figure out. Now, people used to have an intuitive idea about what this was. They used to perhaps even think that it was almost self-evident that there was a God-given notion of space in our minds. Now, perhaps that's partly true psychologically, but in the 20th century, theories of modern physics have played havoc with our notions of intuition when it comes to space. It turns out that the world in which we live in terms of space and time, is much, much more complicated than anything we could possibly have imagined. So there's a direct conflict between intuitive, naive ideas of space and the actual results that modern physicists have discovered, relating to the theories of relativity, quantum mechanics, particle physics, field theories, and more fancy things too. Our large-scale understanding of cosmology and the universe and galaxies and so on also suggests that what's out there is a lot more complicated than we might naively think. So, the world that we live in terms of its space, is probably not extendable, divisible, uniform, and time-independent. Okay. It's not the case that you can just keep chopping space up and it looks more or less the same. That's just not, that you might think that be true, but it's not really what happens. You might think that space just extends naturally in all directions indefinitely. But again, that's almost surely not the case. You might think that it's uniform, that what space looks like here and what space looks like there is pretty well the same. That's also not very clear. In fact, it's wrong. It depends on the masses which are around that curve space. And the idea that space is somehow independent of time is also been laid to rest by modern physics. So it's much more complicated than we might think. And so when we use naive notions of space to base our mathematics on, which is really what we've been doing in this course up till now, we are actually treading a rather thin logical line. In other words, mathematics needs a different framework for space. We cannot rely on our physical intuition to say what space is. And it turns out that the good framework for thinking about it is to base space on arithmetic. Arithmetic is something that's much more fundamental, concrete, easy to understand than the nature of space. So we base our understanding of space on arithmetic. So how do we do that? How do we make our notion of space, our mathematical notion of space, subservient to arithmetic? Well, we've already given the main ideas already. Our pictures of coordinate axes and parallelepipeds and building up a framework using 3 vectors, that already contains the major idea. So the major idea is that a point in space is represented mathematically by a triple XYZ of numbers. We don't have to get philosophical and talk about, well, what exactly do we mean by that point there? For us, mathematically, we're thinking of a point in space, we can just think in terms of defining it as a triple of numbers. What kind of numbers? That's a very good question. And the answer is, well, it kind of depends on us. It depends on what we need to do and what we want to accomplish with our theory. But the best and the most natural number system is the simplest one. The system of rational numbers, which I remind you are just fractions, a over b, where we allow a and b to be arbitrary integers, so plus or minus natural numbers. And with that denominator, b, a over b, is not equal to 0. So the field of rational numbers is a very nice place for arithmetic. That's where we have all our properties, and that's what we generally mean by a number that we're going to be using. Now later on, we extend our number systems. We also throw in some extra numbers as needed. Typically things like square roots, or the number pi, of course, very important, number e, and various other numbers that mathematicians have cause to use. We can add them to our number system, enlarge our number system as required. In fact, a little bit later, we're also going to throw in this magical number I, which is the square root of -1. It's just another way of extending the number system, and that will also be useful for us to sometimes think of three-dimensional space where the numbers involved have things like i's in them. And how do we visualize things? Well, we're going to use our coordinate system that we've been talking about. So we have three lines, x, y, and z, emanating from a common point, which we call the origin, called O. And each one of these lines has equally spaced points on it. And those points are numbered. 1, 2, 3, 4, -1, -2, -3 in the opposite direction. Each of these lines is infinite, and we can also specify rational number coordinates as well. The coordinate system on each line has to be equally spaced, but it doesn't have to have any relation to the coordinate systems on the other lines. And the three lines can be rather arbitrarily oriented with respect to each other, because we're really interested in affine geometry. So I've shown you here that the spacing here in the y direction is a little bit wider than it is in the x direction, and here in the z direction even wider. Now, how are we going to represent points in this system? It's exactly what we've been talking about before, by using parallelepipeds. So for example, the point 3, 1, 5 halves. What do? We go 3 in the x direction, we're going to go 1 in the y direction, and we're going to go 2.5 in the z direction, and we're going to combine those. So we're going to look for the point whose x coordinate is 3, whose y coordinate is 1, and whose z coordinate is 5 halves, and we do that by creating a parallelepiped. Okay, what do? So we go here 3, and then parallel to the y-axis we draw a line, and we go 1 in that direction. 1, that vector there is the same as that vector there. And then from this point we're going to go in the z direction, and we're going to go up how far? Well, 5 halves. So we're going to take a vector that's the same as that vector there, from here to here. We're going to just translate that vector there. So this vector here is the same as that vector there. And what we're getting, this point here is the point A, is just the corner of the box whose sides are 3, 1, and 5 halves. Now, this point is going to be called the square bracket 3, 1, 5 halves. It's a point, not a vector. This is different from what we were doing before. It doesn't look too much different, but conceptually it's different. We are now thinking about actually the nature of space, how we start off the theory. And what we're saying is we're going to start off by creating a system where the points themselves are these ordered triples interpreted in this way. So the concepts of point and vector are different, and we're going to make sure that you understand that by maintaining different notation for points and vectors. So now let's introduce the notion of a vector into our system. Here's our coordinate axes. X in this direction, y in this direction, z in this direction. Here's a point A, which is the point with coordinates 3, 1, -1, so that's actually a point. And here's a point B with coordinates 1, 2, 2. That's another point. We say that the vector V, written A, B, is just the ordered pair of points. So the vector from here to here, which we draw in this way, is mathematically just a pair of points, with the convention that one pair of points equals another pair of points when the 4 points form a parallelogram. So the vector AB, which we draw with this directed line segment here, is the same as the vector CD because the points A, B, C, D form a parallelogram. And now the vector joining A to B, we write that also with a triple, but as a column vector. And how do we get that triple? It's the coordinates of this minus the coordinates of this. 1 minus 3 is minus 2. 2 minus 1 is 1. And 2 minus minus 1 is 3. And these three numbers in a column with round brackets, that's a column vector. That's how we're going to write vectors. So points and vectors in this formulation are quite different things. In many texts and courses, there's no clear distinction between points and vectors. Unfortunately, that leads to a lot of confusion on students' parts. It may appear to be simpler because there's less things to keep track of, everything's the same. But when it comes to applications, it's really important to distinguish between the idea of a point, which is just a particular position, and a vector, which is a directed line segment. Vectors can be moved around, and they're still the same. Points cannot be moved, they're fixed. So it's a very important distinction, and that's why I'm making that distinction very, very obvious in this course. Points are triples written in a row with square brackets and separated by commas, while vectors are triples written as a column without commas and in round vector brackets. The main objects of interest in linear algebra are things that are flat, like lines and planes. So in three-dimensional space, the main objects are points, lines, and planes. Let's talk a little bit about them and the relations between them. If we have 2 points A and B, then they determine a line, the line through them. We use the notation AB to represent the line through the points A and B. If we have 3 non-collinear points A, B, and C, say A, B, and C, then those 3 points determine a plane. And that plane we denote by A, B, C. And typically we will use perhaps a Greek letter like pi to represent a plane. And when we come to represent such things in our two-dimensional picture of our three-dimensional space, the line will usually be drawn just as a line segment. Of course, we can't draw it extending infinitely, so we have to stop at some point. Planes are a little bit harder to draw, but we'll draw them as sort of parallelograms. And again, of course, the planes are going on indefinitely in either direction, but we're going to just represent them by little parallelograms in the representation on the page. If we have 2 lines in space, say L and M, then there are a number of different relations that are possible between those 2 lines. The simplest is that they're actually the same line. We say that they're identical. Another interesting relation is that they're parallel, like this. That means that they span a plane. That is, there's a single plane that passes through both of those 2 lines. We represent that by the usual little parallel symbol. Another possibility is that the 2 lines are intersecting. In this case also there's a unique plane that passes through both of those 2 lines. The other possibility, which is the generic one, if you just choose 2 lines at random, they are not intersecting and they're not parallel either. We call them skew lines. We represent that by something like this. If we have a point and a line, and the point is not on the line, then those 2 objects determine a plane. So there's a unique plane that passes through the line and the point A. So there's kind of a picture of that. There's a line L, a point A, and the plane pi that passes through them both. If we have two planes, say pi and sigma, then there are also several possible relationships between them. If we represent a plane, say, by a book, then the two planes could be identical. It's sort of a trivial case. Or the two planes can be parallel. Something like this. These are parallel planes. They don't meet. And the third, more common pattern is that two planes intersect. So you have one plane like this, another plane like this, and the intersection of the two planes will then be a common line. Alright, so the main thing that we've done today is we've set up a three-dimensional coordinate system, affine kind of coordinate system, to describe three-dimensional space. And in fact what we've done is we've defined affine space in terms of a coordinate system, or in fact purely algebraically just in terms of triples of numbers forming points. So a point is just a triple of numbers, and it also allows us a flexibility of interpretation because we can choose any coordinate system, any three axes or three basic vectors, to set up a coordinate system that will then connect a triple of numbers to an actual point in three-dimensional space. Now, this setup that we've defined, we might call that affine space. The main objects are points and the things that you can form from points, like lines and planes. And we might use the notation A with a little 3 to denote this three-dimensional affine space whose main objects are points. Very closely connected to that, intimately connected to that, is the corresponding vector space, which is subtly different. And a vector is a directed line segment, or a pair of points. So over here, the triple 1, 2, 2 refers to actually this point that we get by forming a parallelepiped and positioning it in the correct way. So that there is just that point. Well, over here in the vector space picture of things, the same triple 1, 2, 2 expressed as a column represents the vector from the origin to that point. Okay. So over here the fundamental object is just the point itself. Over here, that same data encodes the idea of a directed line segment starting from the origin to our point in question. Another example, here's the point B over here, whose coordinates are 3, minus 1, 1. And over here, the same picture, different interpretation. There's the vector 3, minus 1, 1. It's now a directed line segment starting from the origin and going or ending at this point. So this is a very close connection. Vectors and points are almost the same thing. They're certainly labeled by the same kind of thing, namely just three numbers. But our visual or physical intuition about what they represent is quite different. We can talk about lines and planes in either the affine space or in the vector space. And sometimes we'll go from one to the other without perhaps a lot of discussion. But it's generally simpler in linear algebra to think in terms of the vector space. And the reason is because in the vector space we have our basic operations of vector addition and scalar multiplication that we do not have in our affine space. So it doesn't make any sense to talk about the sum of the points A and B. If you have 2 points, talk about their sum doesn't mean anything. But to talk about this vector plus this vector, that does mean something. That has a well-defined meaning. So the vector space has some structure that the affine space does not. Namely, you can add vectors. You can scalar multiply them. That makes the vector space framework preferable for many applications. But you should just be aware that you can easily translate from one to the other. It's really the same picture, except in one situation we're talking about points, another situation we're talking about vectors. Now it's time to have a look at some exercises. Our first exercise we've already discussed is to show that the long diagonals of a parallelepiped all meet at a point. So there is our parallelepiped or box, and a long diagonal, by that we mean a line joining opposite points. Those 2 points, or those 2 points, or those 2 points, or those 2 points. There are 4 long diagonals altogether, and I want you to convince yourself that all 4 of them intersect at some central point. Exercise 9.2 concerns tetrahedron. What is a tetrahedron? Well, it's just what you get when you have 4 non-coplanar points. So if you choose any 4 points, let's choose 4 points here. Say that one, and that one. Those 3, together with this one here. Those 4 points are not all in a plane, and so they form a tetrahedron. That's a configuration. And the question is, how many tetrahedrons can you make from starting off with a basic parallelepiped? So just using the 8 corners or vertices, how many tetrahedrons are there? So we've been talking a lot about projections and pictures of 3-dimensional situations on 2-dimensional page, and it's really good to practice that, so that when you draw points, that you can actually put them in the correct place. There's always a correct place for any point in a 3-dimensional drawing. So just to give you some practice, draw some 3-dimensional coordinate axes, so you can basically draw them however you like. And then with respect to those axes, find points, say A, B, and C, D, those ones with those values, and answer a few questions. Are these points coplanar? So once you've drawn them, just try to visualize, is there a plane that goes through all 4 points? Can you see if any of the 6 lines that are determined by those 4 points, because 4 points determine 6 lines in general, are any of those parallel? Do any of them intersect? And finally, try to draw and label some of the vectors joining these 4 points. Next time we're going to have a closer look at these lines and planes which form the basic objects of interest in linear algebra. We're going to talk about lines and planes in 3 dimensions and how we specify them algebraically. So this is like Cartesian geometry going up from 2 dimensions to 3 dimensions. And it's a very important subject. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.